In this video, we'll talk about the fast Fourier transform and some of its applications. We'll begin with the definition of the Fourier transform that says that any time domain function f can be decomposed into frequency domain coefficients, here f hat, times the complex cosine plus I sine phasors. So let's suppose instead that we sample f in the time domain. So we choose a particular time t sub x that we look at f at. Then we can say that f at this point t sub x is a discrete sum of a bunch of these complex sine waves with their appropriate coefficients. And in fact, we can count the number of samples, of frequency domain samples that could contribute to f. And so this is a discrete expression of the Fourier transform, sometimes called the discrete Fourier transform, or DFT. And the fast Fourier transform is just a particular algorithm for computing a DFT. So here's what I was talking about of having some function here in green that we've sampled at discrete points in time. And here I've said that this axis is power just so I could graph it. But in general, f can be a complex number with both real and imaginary components. And if we take the Fourier transform of that, then what we would expect is that we can have an equivalent representation of our function f, this time in frequency domain and in blue, where this is actually a depiction of f hat here. These are the coefficients that represent this time domain version of f. And in frequency domain, this is essentially a frequency domain copy of f. We have different powers at different frequencies that tell us how much power in the original function is aligned with a particular sine and cosine mode. And just like in the time domain case, in the frequency domain case, generally these coefficients can be complex with real and imaginary components. So by taking a finite window in time domain and looking at f only over that finite window, we take a Fourier transform in that window, and that actually limits how many frequency components we could possibly represent here. On the one hand, the total length of this time window determines the resolution in frequency domain. So it determines whether you can tell the difference between two of the adjacent frequency samples here. And likewise, the minimum spacing between samples in time domain determines the total number of frequencies, the width and frequency domain that you could represent in the spectrum. And that just follows from Nyquist's rule that says that you can only uniquely constrain frequency components if you have 2 samples per period. In general, when you compute a discrete Fourier transform, whether you use an FFT algorithm on your computer or whatever, in general, what it hands you is this, it ranges from 0 frequency up to the Nyquist sample rate, and then it hands you, often in the same array, the range of frequencies that go from the Nyquist sample rate up to the sample rate, or alternatively, you could interpret that as going from minus the Nyquist frequency up to 0. What you'll often find if you just compute a discrete Fourier transform on your computer is that if you put in a function that has both positive and negative frequencies, you'll have to take this window that has both the upper half blue here and the lower half red, and take that red section and paste it back onto the bottom as a negative frequency before you have an accurate representation of your spectrum. Now the question is, how would you actually go about computing the Fourier transform of some function that is handed to you? So a first kind of naive way that you might do it, I say naive, but it's perfectly accurate, is because all different frequencies are orthogonal to one another, what you can do is integrate f against the coefficient that you want, and all of the frequencies that don't correspond to the frequency in that e to the I omega t term, uh, all frequencies that are not equal to that integrate to 0, whereas the frequency that is equal to omega comes out and integrates with some coefficient. So one way that you could compute your coefficient is to say that that coefficient f hat of omega at some chosen omega is just the integral of the function that you wanted, that you were given, f of t, integrated against an e to the I omega t term where this omega matches the omega over here, integrated over time. Of course, this is in the general case. In the discrete case, we have that f hat at some chosen discretely sampled frequency omega sub y is just f at each time multiplied by the value of the sine wave at that particular time for this particular frequency, summed over all the time steps. So a perfectly accurate way of computing the spectrum of f is to simply take f, multiply it by some discretely sampled sine and cosine wave, and then sum up all the time samples to it's essentially integrating over the time window that you're looking at. The unfortunate case is that if you wanted to do this for every single frequency, each frequency has contributions from every single time sample, and so the total computation involved in computing frequencies this way is scales as the number of time samples, n, times the number of frequency samples, which is to say that the computation here is of order n squared. That means it scales as the square of the number of time samples and channels that you're interested in computing. And that's pretty inefficient. It turns out there's a much more efficient way of doing this. The most common way of doing this is something called the Cooley-Tukey algorithm, and I'm not positive that I pronounced those correctly. Under the Cooley-Tukey algorithm, essentially what you do is you separate all the odd and even components of your function. And by odd and even, what I mean are the components that are symmetric around 0 and the components that are anti-symmetric around 0. So just to show you what I mean here, an even mode is one that's symmetric around 0. So it would be some frequency mode symmetric around 0, as opposed to an anti-symmetric mode that looks something like this. So if you do this correctly, what you can do is separate all the different frequency terms from one another very cleverly. The unit of operation that differentiates odd and even functions around a different folding point can be graphically represented in a diagram that's called a butterfly diagram. Now, I'm not exactly sure why this is a butterfly, but the general procedure here is that if you feed in some adjacent samples here, let's say T0 and T1, what this diagram is supposed to represent is that first one of those samples gets multiplied by a complex number, which I'll call Wi here, and I should be clear that this is a W, not an omega. This is some complex number of unit length. And then what this empty circle represents is that you sum the two inputs together here, you add them together, and output the sum on this upper leg, and you output the difference of the two numbers on this lower leg. So essentially what happens is you take 2 points, you rotate one of them, that's sliding the 0 point around to some location, and then you sum them, the two different components, and you difference them. And summing them preserves the even component. If you add together samples that are on opposite sides of the 0 point of a odd function, they will cancel each other out. So you'll get none of the blue coming up here on the positive leg. You'll only get the green. Whereas on the negative leg, if you subtract things that are symmetric around the 0 point, you'll get 0 for anything that's even. But for the odd function here, the blue, you will see that if you difference samples on opposite sides of the 0 point, you'll tend to double the magnitude of the samples there. So as I said before, the key to doing this is computing intermediate results, which is essentially chaining together a bunch of these butterflies in a way where you select certain intermediate points to fold around, certain twiddle factors, and then you can chain a number of these butterflies together to compute an entire fast Fourier transform. So what I'm going to do now is draw a 4-point fast Fourier transform by drawing the butterflies that make it up. So here's a diagram for a 4-point fast Fourier transform, and you'll see that it requires 4 butterflies to perform this fast Fourier transform. So, and they come in 2 stages. Here's a first stage of them that pairs time samples that are 2 samples apart. Here 0 and 2 are paired together, and 1 and 3 are paired together in this lower butterfly. And then in the second stage of the fast Fourier transform, we pair adjacent samples, and I can't call them time samples anymore because there's some intermediate stage here, but adjacent samples are paired together to output frequency samples, and then the next 2 adjacent samples are paired together to output the next frequency samples. So understanding what happens in this first stage, essentially what we're doing is we're asking to differentiate between samples that are separated by half the length of the fast Fourier transform. So we're saying over the entire time window that we're looking at, did we go through an even number of cycles? If so, output the sum on the upper arm of this butterfly. And if we went through an odd number of cycles, output it on the lower arm of this butterfly. Now the next stage in this butterfly diagram asks if over a quarter of the entire window that the Fourier transform is being taken over, did it go through an even number of cycles or an odd number of cycles? Essentially this is asking, was the frequency divisible by 4 or not? And if so, output on the upper arm here, and if not, output on the lower arm. Now the only detail we haven't covered here is what exactly are the twiddle coefficients that are multiplied before we do this summing and differencing in each butterfly. And I'm going to just go ahead and label them with numbers, and I'll draw where on the complex unit circle they fall. So I've labeled all the twiddle factors in the first butterfly stage with zeros, and all the twiddle coefficients in the second stage. Well, the upper one I labeled 0, the lower one I labeled 1. And what these actually are indices of on the complex unit circle. So a complex number of magnitude 1 with the real axis falling in this direction, in the horizontal direction, and the imaginary axis in the vertical direction. 0 is essentially 1 plus 0i. It's something that's purely real. 1 is purely in the imaginary direction. It's minus I. And although it's not used in this fast Fourier transform that I've drawn here, the next coefficients are 2, which splits the difference between 0 and 1, and 3, which splits the difference between 1 and the what's essentially would be minus 1 over here. And you'll notice this is kind of a funny order in that you go 0, 1, 2, 3. Now 4 would actually lie back over here. Here's where 4 would fall, and then 5, and then 6, and then 7. This is a kind of funny ordering. It's called bit reverse ordering. And what it is however many coefficients you have, if you have, say 4 coefficients, 0, 1, 2, and 3, you write them in binary, starting using however many bits you need. So 0, 0, 0, 1, 1, 0, and 1, 1. And then you reverse the order of those bits. So the top one, 0, 0, goes to 0, 0. 1, 0, 1 goes to 1, 0. 1, 0 goes to 0, 1. And 1, 1 is still 1, 1. And then you read these off again. And this is 0, 0. So that is 0. This has a 1 in the 2's place. So that's 2. This has a 1 in the 1's place. So it's 1. And this has a 1 in both. So it's 3. And if you needed to index 8 coefficients, you'd use 3 bits, and that's how you derive that bit reverse ordering. And the reason I go into detail on this is both so you know how to pick out the twiddle coefficients, and I should mention that the twiddle coefficients that you use only 0 of them in the first stage, you use 2 in the second stage, you use 4 in the third stage, 8 in the fourth stage, and so on. So for each stage, you can use exactly the twiddle coefficients that you look up off of this unit circle. And what these are doing are rotating by fractions of periods for each for each sine wave. And in general, you have a number of butterflies in each stage that is half of the total number of points that you are taking a fast Fourier transform over. And then the number of stages is the log base 2 of the number of samples. So in this case, log base 2 of 4 is 2, so there are 2 stages. But if there were 8 samples, there would only be 3 stages here. So in general, the fast Fourier transform is an order n log base 2 n operation. And that is a very efficient algorithm, and I think it may have even been mathematically proven to be an optimal algorithm for computing the Fourier transform in the general case.